So now what we're going to do is we are going to take up a new high level design problem, that is designing a job scheduler. Okay. Now, whenever you try to pick up a new high level design problem, that can be in one of the two situations. First is in a high level design interview that you want to actually appear for you are appearing for a, let's say, some particular MNC or some startup, and you have a high level design interview. In these kind of interviews, you get these questions like designing a job scheduler, designing Pastewin, designing YouTube, designing Netflix, so on and so forth. Or maybe you are actually working as a software engineer somewhere, and then the products that you are working on are actually expecting you to have a functionality in the overall system that, let's say, for example, you are working in an edtech startup, and then in that edtech startup you want to implement kind of like a similar streaming platform that kind of like Netflix has for movies. You want to make it for video lectures. So in those cases also you do system design for the specific features that you are working for. So we are going to look at with respect to both the perspectives, that let's say you have this particular problem appearing in your high level design interview, or let's say in your day-to-day SWE work, right? If in any of these situations things come up, then how you can actually tackle that. I'm going to keep this complete discussion in kind of like, I'll try to divide it in two parts, that what will be kind of like sufficient enough for a high level design interview, where your high level design interview will start taking extremely deep dives, and from where things will look more perspective to your day-to-day job as a software engineer, right? Like what might not be like extremely relevant for your interview perspective. I'll keep all of that, but I just want to make sure that whenever you are designing something, you just don't learn the design perspective with respect to the fact that, okay, I have to just speak up all of this in an interview. I believe if you can try to understand the problem, try to see where that problem occurs, what are the solutions we are actually applying in the solution in the problem at what particular corner cases, then you will be able to kind of like see more value out of these kind of lectures. So without any further ado, let's just start. So the problem in hand is we have to design a job scheduler. Okay. Let's first of all try to understand what is a job scheduler, right? There might be a lot of people who might not know about what is a job scheduler altogether, right? It would be great for them to understand first of all what is a job scheduler. Okay. So when we say a job scheduler, then technically we are referring to some kind of a software or some kind of a program that can automatically schedule and execute a program or a job, right? So you know that whenever you write some piece of code, right, whenever you write some piece of code, that piece of code is referred to as generally what, a program, right? And when you run that program becomes a process, right? Everybody, I believe, knows this part. So you can say job schedule is also a piece of code, or let's say a piece of software that you are going to write, but the capability of this particular piece of code is going to be able to schedule and execute some other program or some other job. Like a job is, you can say, is kind of like a process that you are running, we refer to that as a job, right? These terminologies we'll talk more about, but you can say job scheduler is a software, and you will find this software at in different other softwares already integrated. I'll show you some examples also. So job scheduler is a software that is capable of managing the scheduling of some particular task, some particular program, some particular I would say job, and then execute that as well. Not just the scheduling aspect, but also making it executable, right? That is also the part of a job scheduler. Okay. Now it can be used to run pipelines at specific intervals. Let's say you want to run some reporting jobs. Let's say you are on an e-commerce platform, and then let's say every week you want to run up, I would say a piece of code. Maybe that might be a Python code or a Ruby code. What that code does is it actually consolidates the report of whatever sale has been done on your platform for the last week. What was the highest amount of sales? What were the most number of sale days? What timing were were there where the sale happened the most, and so on. Like you want to generate these kind of reports, right? Or let's say you want to run some kind of a backup scripts, that let's say you have to create backup of some particular data at regular interval, and so on. For these kind of scenarios, job schedulers are very good, right? Now the moment you hear the word job scheduler, if you have been in the programming ecosystem, there is a word named as cron that will immediately pop up in your mind. What is cron and everything, I'll also talk about, and how designing a complete job scheduler is slightly a bit more complex than just saying that, okay, we will set up a cron job for it. We'll talk about all of that, right? But yes, cron is going to be somewhere related to it. If you know about it, that's okay. If you don't know about it, I have some part reserved for that as well. That's the job scheduler. That's what a job scheduler is. Okay, so first of all, let me show you an example. Okay. So I have a real life example of a job scheduler also prepared here. So this UI that you are seeing here, this particular UI that you are seeing, this is from the Azure data factory. This is the Azure data factory, I would say, UI. Okay. If you don't know what is Azure Data Factory, then you can say it's a service that is provided by Azure Cloud. If you want to compare that to something like AWS, then in AWS, you have something like AWS Glue that provides similar kind of a service. What is this Azure Data Factory? What it is capable of? In Azure Data Factory, what you can do is you can set up some pipelines, right? You can set up some pipelines. What is a pipeline? You can say pipeline is just a piece of code, right? And what you can do is these pipelines you can immediately run. Whenever you are setting up the pipeline, you can immediately run. You can see there is a debug button. What you can do is whatever pipeline there is, you can click on this debug button and this pipeline will actually start running. This piece of code will start running. For example, this piece of code can be to copy some data from a blob storage to SQL. Okay, let's say there is a blob storage. From that blob storage, you want to copy the data to SQL, right? Or let's say, let's take more real life example. Let's say you have a data lake. From that data lake, you want to copy the data to a data warehouse, something like that, right? For that, you will be writing some piece of code. And this pipeline is referring to that some piece of code. Now, maybe you want to run that piece of code immediately for testing purpose, but this is not the actual case for here. This is not the actual case why you will write this pipeline. The actual case will be that probably you are writing this pipeline because you want to run it again and again at a specified schedule. Let's say every week on Monday, 10 a.m. in the morning, you want to run this particular pipeline. You want to set up that. So you can see there is an option of adding a trigger, adding a trigger. What is this trigger in this Azure Data Factory? This trigger is a mechanism with which you can do the scheduling. This trigger is the mechanism, right? This trigger is the mechanism with which scheduling will be done. Right. So this to set, so the problem that we have in our hand is designing a job scheduler. You can say this particular feature of adding a trigger so that you can run this particular pipeline is the implementation of designing a job scheduler. Okay. More examples can be, you might have seen dedicated emailing platforms where you can set up your email templates and then send emails all together. Okay. So on those emailing platforms also, you can schedule the emails. Let's say every day 10 a.m. in the morning, you want to send some emails all together and so on. So what we have in our hand is we want to set up a job scheduler, which is capable of handling end-to-end scheduling of the job and then execution of the job. So we want to have a complete end-to-end system developed where we can actually schedule the jobs and execute the corresponding jobs. I hope with this much introduction and with this real life example, you are now able to understand what is a job scheduler altogether. So now, considering the fact that we have set up the base foundation of what job scheduler is, then you can see there is a small job scheduler workflow that you are able to see in front of you. Okay. So you can see this is the job scheduler system that you are going to develop. This component is representing the job scheduler system that we are going to develop. Okay. Now, inside this job scheduler, there can be different mechanisms with which the jobs can be triggered. For example, there can be time-based triggers. There can be time-based triggers. Time-based trigger means that, let's say, every Monday 10 a.m. in the morning, do this job or do this task. Okay. This is kind of like a time-based trigger. Time-based trigger means that you want to run a particular job at a particular time or on particular time intervals. Then there is event-based triggers. What is event-based triggers? That let's say you have some, you in your system, or let's say in your broader ecosystem of the software, the whatever you are working with, there is a event that happens, right? For example, let's say if some data is loaded in, let's say, your S3 bucket, then process it. Okay. So let's say there is an S3 bucket. Inside that S3 bucket, what happens is that you keep on adding some video files and you have to process that video files, but you don't want to immediately process the video files. So what you can do is you can kind of like create a job schedule for that, okay, the moment video file gets uploaded to S3, at that moment we are going to schedule a job that, let's say, in the next 24 hours, whenever you have some time, you can start processing this video file. So that will be event-based triggers altogether, right? So there can be two type of triggers: event-based, time-based. And a special case of event-based would be that somebody comes up and just manually want to run the job, right? Manual run will also be kind of like an event that somebody came up and manually run the job, right? So these will be the kind of triggers. And then what the job scheduler is going to do, whatever tasks it has been given, it will try to schedule that, right? It will try to schedule that. There can be different type of tasks. For example, one task can be to, let's say, create a backup. One task can be to create reporting. Let's say you have to create reports of the sales and everything all together. Some task is to, let's say, do some data processing. Let's say there is a video file, you want to process that video file into multiple different formats, or let's say multiple different resolutions altogether. All of this different kind of, I would say, task will be given, and this job scheduler is going to schedule that on the expected time altogether, right? This will be the regular job scheduler workflow. And a lot of times you will hear these two words in the ecosystem of a job scheduler, that is a task and a job. Okay, what is a task? Task is some functionality to be executed. Task can be sending emails, task can be processing a video, task can be creating reports of your sales, and so on. What is a job? Why this word job again and again comes into the picture? Job will be the final actual process that will be running in the memory that holds the code of what task is expected to be done. For example, your task is to send emails. Now you'll be having some script, or let's say some mechanism with which you will be sending up the emails, right? So let's say you have some Python code to do that. So taking that Python code, loading that into the memory, creating a process out of it, and then making that process run. This running process, this actual final process that you have in your memory, is referred to as a job. So whenever we say job scheduler, we are technically referring to something like this. Okay. So this sets up our premise. This sets up our premise that what a job scheduler is. Okay. Now, of course, when you are actually in an interview, then probably you won't be spending this much amount of time in actually understanding what is a job scheduler. If somebody gives you a question that what job scheduler is, then probably you can ask for a couple of details that will be wrapped up probably in 10 to 20 seconds only. They will tell you that, okay, job scheduler is going to be a system that can schedule and execute a program or a job for you. These jobs can be, let's say, running some pipelines at specific intervals, running some reporting job, running some backup scripts, etc. This much data will be technically given to you in an interview. The remaining, I would say, pointers I have told you so that you are able to better understand the complete solution, right? But generally in an interview, you won't be given this detailed description of a general system, because most of the people know about these systems if you're already working in a software engineering ecosystem, right? Because the problems are, let's say, designing Pastebin, designing job scheduler, designing Netflix. So you know about these systems, but yet in case if you're not aware about what job scheduler is, I believe that clarifies everything around the job scheduler workflow. Now, let's start setting up the functional requirements. So for any design problem, it's great that we set up the functional requirement, that what are the functionalities our system should be able to do. Okay. These functionalities will be the core final functionalities that we want to develop. Okay. It is generally a good practice, again and again, I generally repeat it in all of my discussions, that you try to keep the functional requirements as minimalistic as possible, compared to the, considering the fact that you have a 1 hour round in which you just barely get 50 minutes to do the complete high level design. So don't just do over committing of the functional requirements. Keep this thing in mind. I might have kept a couple of extra requirements because we have a lot of time, but in your interview you should be keeping all of these things in your mind. Now, what is a functional requirement? Functional requirement is the final actual functionality that our system should be able to execute. Okay. So what are the functional requirements that we want to have? A user can submit a job to run based on a particular schedule and see the status of the job. This is the most important functionality, very important functionality, because this is the core functionality of the system, that user should be able to submit a job, right? And then see the schedule of that particular, or I would say set the schedule of the job, that let's say every day 5 p.m. in the morning this job should run, and then later see the status of the job, that what happened when you with the last run of my job, right? Something like that. Then maybe if you can, then you can also try to support a manual trigger should also be there, so that somebody can come up and manually trigger the job. For example, something like this debug button, right? That you click on this debug button and you are able to run the job. We don't have to discuss the UI perspective of it, but overall, I would say the backend perspective of it, that how manual trigger would be implemented. This is a good to have thing. This is a good to have thing. Why good to have thing? Because this is very simple to develop, right? So even if you do not discuss too much on it, it's going to be good to have. Okay. Then every submitted job will be a Python script. For now, what we will assume that whenever somebody is going to submit a job, that job is going to be a Python script. Why I'm doing this? Because we should also restrict the, I would say, possibilities in our design solution. Otherwise, there will be too many variable things going on here and there. That's why I've written. Later, you can add support for more languages like writing a Ruby script, writing a Node script, writing a shell script, etc. But for now, what we are going to do is we are going to support only a Python script. That let's say if somebody has to schedule a job, what they're going to do is they're going to upload a Python file to us in which the complete job has been written, and then it will be our responsibility to run it on the expected schedule altogether. Okay, cool. So this is going to be important. This is going to be important to mention. Okay, then this one is very, very important. This fourth one is very, very important altogether. Each job should run at least once on the given schedule. Now, our system should be able to promise the fact that if somebody has been able to successfully create a schedule of a job, then it will be the responsibility of our system to have a guarantee. We are trying to provide our users a guarantee that our system will be able to run the job at least once, right? Our system should be able to run the job at least once. We are going to see the perspective that what happens if it runs more than once, how can we avoid that altogether. That should be a relatively simpler problem to solve, but this guarantee we need to provide that at least once we are going to run the job for the given schedule, right? Because if there is if it happens that let's say somebody scheduled the job and at that particular expected schedule the job didn't run, then that can be a problematic scenario. So this is going to be a guarantee that our system is going to give. This will be a guarantee that our system is going to provide, and this guarantee is expected to be discussed in the interview. And then jobs can be recurring also. That means it's not like somebody says that okay, I have to run the job 5 days from now. It's not like that. Probably somebody will say that every 5 days I have to run the job. So jobs can be recurring, right? And then we should also try to provide a support for disabling the job runs, right? That let's say if somebody don't want to run the jobs anymore and let's say want to set up a like wants to set the status of the job as disabled. So a disabling mechanism should be there so that if a job is marked disabled, you should not run the job. This will also be relatively more simpler to do, but this is important. Recurring support, this is going to be very, very important to technically discuss. Okay. Some good to have features, some more good to have features can be there, that you can support resource allocation configuration. Resource allocation configuration means that let's say this job is going to be a Python code which you are going to run. Now this Python code is going to run on a machine, right? Just think about it. This job, when I initially mentioned, then I told you the fact that every submitted job will be a Python script, so it will be a Python code. This Python code is going to run on a machine, right? So it will be a good to have feature. If you want, you can discuss that how can you support resource allocation. That let's say if the user wants that okay, my Python script or my job should run on a more powerful machine, if you can give a configuration related to that, that would be good to have, but not very important to discuss in the interview, because this will be relatively very simple to set up. Log monitoring support, that you are able to provide dedicated logs for the corresponding jobs, and monitoring dashboard support, that people are able to do more monitoring on the jobs. These are going to be good to have features, right? A lot of things will be very straightforward to think of, but again, not very important, but yeah, good to have. Okay. And then an interesting feature will be to support dependent jobs. That let's say if somebody has three jobs but they don't want to run the three jobs parallelly, they want to ensure that first the first job runs, once the first job is completed then the second job runs, and then the third job runs. So kind of like a support for dependent jobs, right? That there is a job A, after job A completes you run job B and job C, and after job B and C completes then you run the job D. This kind of a dependency graph you are able to support. This is going to be again an important feature, right? This will not be important for all the levels, probably. Like if you are interviewing for let's say SWE2 role, then it will be okay if you don't even discuss this. But if you, let's say you are appearing for a senior engineer role, then there would be a good chance that somebody will expect you to give the support of the dependent jobs altogether. So these are kind of like the functional requirements that we are going to have. Again, depending on how much time you have in the interview, you can pick up some of these and at least pick up the very, very important ones. So here you can see there is a small diagram that can help you to understand this kind of a dependent job scenario, right? That let's say you have a job one Once the job 1 completes, then it triggers job 2. Once job 2 complete, then it triggers job 3. And once job 3 complete, then it triggers job 4. So every job is going to separately run, but one after another. And this is our job scheduler system, which should be able to handle these kind of dependent jobs, right? Make this, keep this thing in mind. Now let's start talking about the non-functional requirement of the system, because this is going to be important for us. Now, the system is expected to have high availability, right? Availability will be more important for us rather than consistency. Why? Because just think about it. People should be able to come up and like schedule their jobs, and at the expected schedule time, the job should run. Now, what happened with the job, the status of the job, even if you don't have the latest update on what happened on the job. For example, let's say the job completed 5 minutes back, and let's say you do not have like the immediate update of that, that's gonna be almost okay for us, right? We are going to provide more availability in our system, that whatever jobs are expected to run, they will be running at the required schedule. Our system will be available. Our system will not be down for that particular amount of time, like for a huge amount of time, so that the jobs are not running, or let's say somebody is not able to even schedule a job. So availability is going to be something that is going to be more priority for us. This is something that you can discuss with the interviewer, that what is more priority for you in the current system. I believe that availability should be more important for us. Very, very important is this guarantee that we are going to give, that at least once our job should run, right? This guarantee should be there, right? This is kind of like important. Now, one very important and interesting thing, the job should execute almost when the schedule run is expected. Let's say you are expecting the jobs to run at 10 a.m. in the morning. So almost 10 a.m. in the morning, it should execute. We are not going to put a hard bound deadline that, okay, exactly 10 a.m. if it didn't execute, then things are going to go too far. Maybe a 2 to 4 second delay is also okay. Maybe slightly a bit more, maybe 5 seconds, 7, 8 second delay is okay. But it should not like be delayed too much. Like 10 a.m. in the morning, we were expected to run a job, and let's say it's running at 10:05. This will be like too late for us. So we can have a config like delay in the agreement, that some delay will be there. A few second of delay we can actually have, but it should not happen that the job has not run. That's our important part. That's where the availability to consistency comparison comes into the picture, that we are not going to like guarantee that, okay, 10 a.m. exact sharp dot maybe it will execute, but yeah, 10 a.m. let's say 5 second 10 second delay will be there. So consistency will not be our highest priority, but availability will be there. That means the job will run, guarantee will be there, the job will run, it will create the output, it will get some error, something will happen with the job, but the job is going to technically run, right? This is going to happen, and we are going to ensure that we do not have a lot of resource crunch. How we can handle that, I'll talk about, I would say, the provisions that you can set up with the corresponding system. Okay. And then if the job scheduled to run is delayed, we must at least alert the user, right? In case due to any XYZ reason, because you also no system guarantees 100% availability, right? Let's say you are guaranteeing, let's say 5/9 SLA or 6/9 SLA availability. So there will be, let's say, a couple of minutes in the few in the whole year when you might not be available. In case there was some delay from our system side that made a job to run in slightly more delayed fashion, then there should be an alert that should be given to the user. This is again a good to have feature. Again, just think about more good to have features. If you have time, you can discuss about them. Okay. An important part, what scale are we looking at? What scale are we looking at? We should be able to run approximately 10 billion jobs per day. This is going to be the scale that we are going to handle, that our system should be able to handle 10 billion jobs per day. This is a metric that probably your interviewer will give you, or let's say if you're working, then you know what system you are developing. So what is the requirement for your system? So 10 billion jobs per day is going to be something that you are going to scale your system for, right? This is something that you have to keep in mind. Now let's try to do some math. To be very honest, some more math will be coming up later. This is just like a fair amount of idea around what kind of a throughput and everything we are expecting in the system. So we'll be doing a back of the envelope estimation altogether. This estimation is good to do in an interview because it shows the depth of I would say problem understanding to you, right? That how much you are able to understand the problem, or how much any system you are able to understand, or how much due diligence you show while you're designing a particular system. Okay. So what was the throughput that we were expecting? We were expecting our system to be able to handle 10 billion jobs. If you look at the number 10 billion, it looks like very, very high. But let's see if 10 billion jobs per day we are looking at, then what's the throughput? So you can say that if you have 10 billion jobs, then approximately you have 10 raised to the power 9 kind of jobs per day, right? We can assume more or less 10 raised per 9 jobs per day, right? So you can just check. If you don't know the numberings around million, billion, and everything, I'll just show you. So you can say 1 million in power of 10. You can just keep these numbers in your mind, right? You can see 1 million is 10 raised per 6. So 1 billion will be what? 10 raised per 9, right? So I'm keeping the assumptions around with respect to 10 raised to the power 9. And whatever numbers we get, we can just multiply that with 10. I have kept the complete calculation with respect to 1 billion. I have kept the complete calculation with respect to 1 billion. Now, whatever will be the interviewer's expectation, let's say interviewer says you have to handle 0.5 billion jobs per day. You have to handle 1 billion jobs per day. You have to handle 2 billion jobs per day. You can just multiply that value X with your final calculation. This complete back of the envelope and estimation I've done with respect to 1 billion jobs. Okay, cool. So 1 billion is 10 is per 9 jobs per day. And if you calculate how many seconds you have in a day, approximately you have 10 is per 5 seconds, right? Again, everything is an approximation number. So if you divide this, you will get 10 raised to the power 4 jobs per second, right? This will not look too high of a number, right? Considering initially you were at a billion jobs. And then again, if you have 10 billion, that means this number will go to 10 is per 5 jobs per second. Again, you can scale up, scale down accordingly, whatever number has been given to you by your interviewer. Okay. So let's assume that, okay, we have 10 is per 4 jobs per second altogether. Now we are going to spend some good amount on the storage as well. Why? Because every job that we have is a Python script. So how much storage we are going to like at least spend on if we have this high amount of jobs coming up? So assuming that every job is kind of like a unique job, because if you have non-unique job, then that means two jobs have the same Python script, right? But assume that let's say all 10 is for 9 jobs or something like that is unique. So again, 1 billion jobs, again, the calculation is with respect to 1 billion jobs. So assume you have 1 billion unique scripts stored, which runs daily, and each one has average 200 lines. So you have to do some approximation that let's say on an average a Python script, already Python is very concise in terms of code. So 200 lines will be more or less good even if you're writing a PySpark script or something. So 200, 250, 100, 150 lines are good. I took an average of 200 lines and each line has approximately 50 bytes of data, assuming. So you are going to have 200 into 50, that means 10 KB approximately per script. 10 KB per script and you have 1 billion script, this will make up to 10 raised per 13 bytes. 10 raised per 13 bytes is going to be approximately 10 terabyte of data, right? I believe if let's say you have to dump these scripts in a good storage, a blob storage or a data lake service like S3, that would be pretty simple to do, right? Not much of a hassle we are going to see, right? But I believe a straightforward storage solution, right? Straightforward storage solution will be around S3. Now, a good question can come to your mind, is this daily? So you can say that if 10 is per 9 jobs are getting scheduled in your system, then there are two cases. Either these are recurring jobs. If these are recurring jobs, that means we can assume that overall only we have unique 10 is per 9 jobs across the year. They just get scheduled daily, right? Because these are recurring jobs. That's the scale that we are handling, right? If they are not recurring, then of course we'll be having lesser number of jobs. But we will never be having more than 10 billion jobs. So the 10 billion unique jobs are going to be there. So the total number of scripts that you have to store is going to be nothing more than 10 TB altogether, right? It's not like daily new 10 billion jobs or new daily 1 billion jobs are going to come. That's not the expectation. Daily we should be able to run 10 billion jobs or 1 billion jobs, whatever number you are going to take. If you're going to run, because that's how scheduling works, just think about it. If you see any particular system, then whatever jobs or whatever reports or whatever backup scripts that you have to create, right, all of them are going to run. It's not like daily new scripts come up. It's not like daily new jobs come up, right? Probably initially you start with probably every team gets 100 odd jobs allocated, you have 10 is per 5 jobs, then slowly and steadily they get more jobs, more teams come up, and eventually the biggest scale that probably your complete system is going to handle, that in one day it should be able to handle running of 10 raised to the power 9 jobs, or 1 billion jobs, or let's say 10 billion jobs if you want to scale up to one more factor of 10, right? So even that is going to be the expectation. This is the expectation that you have to keep in mind, and that's why I said that probably you are going to have 10 terabyte of data, more or less, give or take. So a good data lake service, or let's say a blob storage service like S3, is going to be good to have thing here, where you can technically store all of this data. So with that, let's see what are some core system entities that we are going to look at. It would be good in this particular problem to list them down, because we'll be talking about them a lot. So you can see there will be a user, which will be the owner of the job, who creates the scheduling of a task, right? How user authorization is going to work. We're going to keep it out of scope, because of course in a 1 hour interview, you cannot discuss authorization, authentication, plus the core system. So assume that user auth and everything is already in place. Then there will be a task. Task is going to be referred by the Python script, because remember, what is a task? Task is the actual thing that you have to do, but when you run that task, it becomes a job. So Python script is going to be referred as the task, and the job is going to be an instance of a scheduled task. That means what task you have, that means what Python script you have, plus what schedule you want to run this Python script on, plus what parameters you want to run this Python script on. This is going to be important, that you should be also considering that your Python script is not going to have like hard coded parameter. Probably some parameters will be provided by the job owner, that on what parameters this Python script should run. This will be a job entity. This will be a job entity. Then there will be an entity we will refer as run. What is a run? Once a job runs at a given schedule, we are going to create a run entity for it. For example, let's say a job is scheduled to run in every 1 hour. So the job DB, or the job storage, will be just keeping the data of what Python script to run, when to run, with what parameters to run, and who is the owner. When the job actually runs, let's say if it has to run every hour, then it will run 24 times in a day. If a job is running 24 times in a day, then in the run storage, we are going to have 24 entries for that job. What happened with every time delta, whether the job was able to successfully run, not run, what happened to that particular run, is going to be this run entity. So run is going to identify one successful, one failed, or one pending, but one actual run of a job. This is going to be important, right? And then there is an interesting data storage that we are going to have, which is going to be job schedule. This job schedule is going to have the schedule of the upcoming runs. This run table, or whatever storage we are going to develop, this is going to tell what happened with the previous runs. Let's say you want to see what happened with the last 20 runs of this job. Now if you want to see, okay, when is the job next scheduled, that schedule we are going to store in job schedule storage. So this is going to store the exact timestamp for the next run of the job, because what the owner is going to tell you, owner is going to tell you that run this job every 5 hours. But in your system, you need to have this specified, that what is the meaning every 5 hours. That means first the job has to run at, let's say, 5 p.m., then the job has to run at 10 p.m., then the job has to run at, let's say, what, 2 a.m. in the morning. That will be at 5 hours, right? So 2 a.m. in the morning, and so on. So you need to have like those exact timestamps, right? So this job schedule storage is going to store the exact timestamp for the next run. So you can say this is more or less going to refer to the past runs of the job, and this is going to tell you what are the upcoming runs of the job, right? This is going to be important for us to technically store, and these are going to be the core system entities that you should try to handle. So one approach generally I take in an interview is that once the I would say back of the envelope estimation, functional and non-functional requirements are set up, I generally try to go with a basic high level design, like at least start developing some diagrammatic representation of how you see the system to look like. Okay, so let's start with that. Now, user should be able to create or schedule your jobs. See the first functional requirement. First functional requirement was user can submit a job, right? This was the first functional requirement. User can submit a job altogether, right? So if user is able to submit the job and then see the status of the job, let's at least try to set up the, I would say, premise for this one, right? So how things are going to work? Very, very basic system architecture we are going to go with. There will be some client, probably a browser client, where the user can come up and do the scheduling. The user will send the request from the client. The request will come to an API gateway. API gateway is the component. If you don't know, I'll just quickly skim through. Is a component that will be responsible for doing all the rate limiting, doing any kind of authentication required, and so on. Once API gateway passes the request will go to a load balancer. Why? Because we are going to have a couple of services which we will name as scheduler service. These scheduler service is going to be, let's say, a microservice for us, which will handle everything around scheduling a job and seeing the status of the job, nothing else. This scheduler service is not going to be responsible for actually executing the job. Keep that thing in mind. So the responsibility of the scheduler service is to create job schedules, One will be to see job status. It will not handle execution, not handle job execution. Why this is not going to handle job execution? Because job execution can be very heavy task to do. If you do the job execution also on the same machine where you are running the scheduler service, there can be a chance that the overall machine can be overloaded with the task, right? So it's better that because we also want to ensure high availability in the system, right? So it should not be a case that user is not able to schedule a job. User should be able to give you the request of the job schedule and we should be able to accept it. The job running will be happening in different machines so that we do not hamper the machines going on altogether. So let's say we have a horizontally scaled scheduler service, right? And we have a load balancer in front of it, which will be able to redirect the load. And whatever data to create a job the user is going to send, all of that we are going to dump in a database. What database we should pick, what DB we should pick, we'll talk about that. What DB we should pick, we are going to talk about that in a moment. But this should be a regular client server flow, right? That a request is going to come up from a client, we'll authenticate and rate limit the request, we'll forward it for the scheduler service. Scheduler service will be responsible for taking this job altogether. Okay, cool. Now, to create a job, what are details the user is going to give? So the user is going to maybe have a API like this. So let's say there is a post request of /API/v1/jobs, right? This kind of a post request they can actually send, right? And for querying the jobs, let's say there will be, let me write it here. For querying the jobs, there will be, let's say, a get request to /API/v1/jobs, and then there will be a unique job ID, right? On this particular route, you can actually give the status of the job, right? Something like this. So you can see I have given the API here, post request API v1 jobs. Why post request? Because we are going to create an entity, or let's say we are going to add some mutation altogether. Now, how this post request body is going to look like, what the user is going to send. The user is going to send a task ID. Now, what is this task ID? This task ID can refer to the Python job or the Python script that we want to run. So every Python script, let's say, will be having a unique ID and we'll be storing the Python script in some S3 storage altogether. Then you are going to send a cron. What is a cron? Cron is a string expression that you can use to represent some kind of a schedule. If you don't know about crons, wait for a while. I'll talk more about crons in some time. But you can say this cron parameter is going to be the one which is going to tell you the schedule to run the jobs. And then you can send the parameters. What parameters you want to send to run the job. This will be the request structure of your job create API. This is important in your system design interviews. Please do not miss your API designs, because those are like bare minimum. Like even interns know how to design an API, right? So you should not miss that. Okay. And we are not going to put a restriction that two different users are not going to use the same task ID. If two users want to use the same Python job, they are okay. We are going to support every job is a unique job, but if two users use the same Python script, it will save some space for us. So we are not going to put any kind of a restriction. If your system, let's say if the interviewer asks you to implement that or discuss about that implementation, you can do that. That should be a fair enough thing to do. You just, before you create a new job in the database, you just have to check whether there is already a job with the same task ID or not. If it is, then you can reject the request. These are going to be, let's say, relatively very straightforward request to go for. But you can see this is going to be the request payload. This is going to be your route signature, and this is going to be the type of the request. And that's what we are going to do. So users can make a request to schedule us to the scheduler service, telling the task ID and the cron schedule for running the corresponding job. Right, we are going to send the request to your API gateway. API gateway will forward it to load balancer after every auth and everything. And then we are going to redirect the request to the scheduler service. One of the I would say EC2 instances, let's say we have, is going to pick up the request and going to update that in the database. How the database will look like, how the storage will look like, we'll try to find it out. The other API, which is important, is going to be the get request to query the status of the job. This will be a straightforward get request to /API/UN/job/job ID. You will put the job ID and it will return you a response. You can prepare the response structure as well. So response structure for this should look like, let's say there will be a job ID that you are going to return, and then there will be a status of the job, that what happened with the corresponding status of the job. This should be kind of like a bare minimum response payload that you should return for the get request altogether. Now, the most interesting thing that we are going to have here is how the database should look like. Okay, I've already dropped a hint here, but let's see how things are going to work. Okay, so let's start doing the database discussion. This is going to be slightly more deeper. There is a good chance that, let's say if you are interviewing for a SD2 role, this deep discussion might not happen too much. Yes, there will be a discussion on what database you are choosing, but the amount of depth that we are going to discuss might not be there for a SWE2 role. But let's say for senior roles, you can expect this much amount of discussion. Also keep one thing in mind. If you are not able to justify what DB you are choosing and why you are choosing, then there is a good chance you are going to get rejected, because some interviewers do expect you to not just tell which DB you are going to pick, but also have a good reasoning for that. So we'll see. DB discussion. Okay. So for our job scheduler, we have a need of high available database. We need to ensure high availability. Okay. So let's decide that what can affect the availability. What can affect the availability in the database? There are only two main operations in a database, either a read or a write. Okay. You can either read the data from a database or write something to the database. Okay. Okay. Cool. Now, let's see what are the operations from which our writes are going to come up. Let's try to figure that out. If we know from where our writes are going to come up, maybe we should be able to make a decision. So one kind of write to the database, write and considers everything, creation of a data or updating of a data, both I'm considering in write. Scheduling a job. When somebody wants to schedule a job, that will be one instance when a write is going to come up. Second, creating a run for the job. Whenever you start running a job and let's say the job run happens, or let's say you are going to create a job schedule. Remember the entities? We have a run entity that is going to denote the past, a job schedule entity that is going to denote the future or the upcoming jobs. So whenever you are going to set up these kind of runs, that what happened with the last run or when the next run is going to happen, that's where a writer is going to come up. And then when a run happened, what happened with that run? For example, there is a job. You pick up the job and start running. So what you should do is you should update this run status as running, that we have started running the job. After 4 hours, the job completed. And then you got the status as a success. Then you should update that run. Whatever run that was, you need to update that run that, hey, we have technically successfully completed this job. So the status of the job will be updated from running to success. Or if it is failed, so running to failed, right? So these kind of updating we have to do. This is one more type of a write that we can see. Now let's try to figure out how the reads are going to come up, from where our reads are going to mainly come up. So our reads are going to come up when we have to prepare a mechanism with which we will fetch the upcoming jobs, right? Think about it. One type of read in our system is going to come when some component of our system is going to read the database and see, okay, what are the next set of jobs to run? Where will be the next set of jobs present? In the job schedule, right? So in the job schedule, we are going to keep the next set of jobs that are, or I would say the next upcoming job events that we are going to run. So this will be one read, right? This will be one type of read that, okay, some component of our system is going to query the database and see what are the next set of runs that are going to come up. The second type of a read is going to come up if the user queries the job status. User wants to see what is the job status that is going to come up. Okay. If I try to see which one of these are very heavy, I can definitely see this is not too much. This is not going to put too much load on your servers, right? Generally, in a system where you schedule jobs and expect a job to run, you don't just go and every second hit 100 queries and say, what is the status of my job 100 times in a second? You don't do that. Probably you will check a status of the job. If it is running, you will come after 5 minutes, check it again. So it's not going to put a lot of load. Definitely, this is not going to put a lot of load. So we are more or less okay with this. These remaining four parts, that means these three type of writes and this one read, we have to decide which one of these is going to put more load, so that we can decide, is our DB going to be a write heavy DB or is our DB going to be a read heavy DB altogether. Now, having all of these, let's see what the choice of the database is going to depend on. So the choice of DB will depend on how frequent we want to fetch the upcoming jobs to run. Can I say that? Because this is the only read heavy part. This is the only part which is going to be more or less a read heavy part. If this is not going to be a too much load on our system, that means we have these writes and these writes are good heavy writes. So we can say it's a more, with respect to the amount of read, it's a more write heavy system. So let's take a call on this. Let's take a call first of all on this, which is a mechanism with which we will fetch upcoming jobs to run based on the schedule. So that's why I've written the choice of the database will now depend on how frequently we want to fetch the upcoming jobs. Just think about it. Just think about it. So let's say, we have a job one, right? We have job one, which was expected to run every 5 hours. Every 5 hours. Okay. We have job two. This is also expected to run every 5 hours. Or let's call it as every 5 minutes, maybe. Let's say. And we have a job three that is expected to run every 2 minutes. Okay, something like this. This is what a schedule is going to look like. So now what should happen if, let's say, it is 3 a.m. in the morning. Let's say this timestamp T1 is 3 a.m. in the morning. Okay, so now what should happen is at 3:02 job 3 should run. Then at 3:05 job 1 and job 2 should run. And before that, once again, before that, at 3:04 job 3 should run again. At 3:04 the job 3 should run again. Then at 3:05 job 1 and job 2 should run again. Then at 3:06 job 3 will run again. Then let's say at 3:08 job 3 will run again. And then at 3:10 job 1, job 2, job 3, all of them are going to run again, and so on. They'll keep on running. This is how a schedule is going to look like, right? So now just think about it. Our system should be capable of handling the fact that it should know what all next set of jobs to run. Our system should be able to figure out what all next set of jobs to run. Our system should be able to self-determine that, okay, at 3:02 run J3, at 3:04 run J3 again, at 3:05 run J1 J2, at 3:06 run J3, at 3:08 run J3, at 3:10 run J1 J2 J3 all, right? Our system should be able to determine that. So we can say that we need to determine, or we need to decide the DB depending on how frequently we want to fetch the upcoming jobs to run. Okay, so now you will be having a job schedule DB. You will be having a, let's say, job schedule DB. This job schedule, if you remember, keeps the exact timestamp of the next runs, exact timestamps of the next runs. So let's say there is one entry inside this job schedule which is going to say let's say it is going to say J3 at 3:02. Then one more entry will be there, J3 at 3:04. One more entry will be there, J1 at 3:05. One more entry, J2 at 3:05. Then J3 at 3:06, and so on. So let's say we are going to store this kind of a data inside our job schedule storage, right? Which tells which job is going to run at what particular point of time. We can keep this schedule. Okay, cool. So what do we need to do? We need to query this data. We need to query this database and somehow let's say every minute, we will fetch all the jobs which are expected to run within the next 1 minute. Think about it. I'll say at 3 p.m. or I would say at 3 a.m. I will try and query my database that in the next 1 minute, what all jobs are going to run. Okay, no jobs are there. At 3:01, I'll ask in the next 1 minute, what all jobs are going to run again with this database. So after 1 minute, I queried the DB after 1 minute. Then after 1 minute again, at 3:02, I'll ask what all jobs are going to run, right? I'll say there is one job that is going to run. Cool. At 3:03 again, I queried what all jobs are going to run. At 3:04 again, I queried what all jobs are going to run. At 3:05 again, I queried what all jobs are going to run. For 3:05, I will get J1 and J2 and so on. So let's say every minute, and this can be a configurable value. You can keep it 2 minutes if you don't want to put a lot of load. If your system is able to handle your loads gracefully, maybe you can keep it 30 seconds, right? I'm keeping a good figure as 1 minute, that every minute our system will be querying this job schedule database and ask that in the next 1 minute, what all jobs are going to run. Because if we have all the next set of jobs that are going to run in the next 1 minute already loaded in the memory, then we will be able to operate them on a bit faster, right? We don't want to be in a situation that every second, like at 3 a.m. 1 second, we query the database that is there a job to run at 3:01, 3:01 and 1 second, and then in the next second again I query the DB. I don't want to query the DB again and again, right? I don't want to query the DB again and again. It will be too bad for us, right? It will be too bad for us that you keep on querying the DB again and again. Let's say you query the DB once in 30 seconds, or let's say a good metric can be once in 1 minute. And in that query, you figure out what all jobs you are expected to run in the next 1 minute. Because we already have the SLA of plus 3-4 second delay, right? So even if there is a millisecond delay here, no problem. Like we'll be able to manage. So at 3:05, we know that from 3:05 to 3:06, we have to run J1 and J2, right? We have to run this. So every minute we are going to query the database. Okay. So you can see. So let's say that we query the database somehow that every minute to fetch all the jobs which are expected to run within the next 1 minute. And once we have the list of the jobs that we are going to run in the next 1 minute, then somehow we are going to sort these jobs based on their scheduled time. That let's say one job was expected to run at 3:05 10 seconds, right? One job was expected to run at 3:05 12 seconds. One job was expected to run at 3:05 20 seconds, and so on. So this will be, let's say, arranged in terms of their scheduled time. They will be arranged in terms of their scheduled time, and then we can arrange them in a FIFO fashion, first in first out. That means whatever job is expected to run first will be, let's say, arranged first, then the job that is expected to run after that, then the job which is expected to run after that, and so on. If two jobs have same time, then we can just keep them in any arbitrary order. It's not going to matter for us. Okay, cool. So this is a nice hook for us. This is a nice hook for us, that we would like to arrange our next 1 minute jobs in order of their scheduled time in a FIFO order. We don't want to be in a situation that, okay, a job was expected to run at 3:05 10 second. One job was expected to run at 3:05 20 second, but we ran this job first. No, right? We don't want that. We don't want that. We want to be in a situation, let's say you have a job at 3:05 10 seconds, then you have a job at 3:05 20 seconds. So this job gets picked first. Once this job has been picked, then you pick the next job altogether. So we want to arrange them in a FIFO fashion. What options you have for a FIFO fashion? A straightforward DSA solution would be some kind of a queue, right? Some kind of a queue. Okay. So what options you have to implement a FIFO option? Immediately, you might think of some kind of a queuing infrastructure, and a lot of you guys will start talking about Kafka. Okay, Kafka will be a good streaming mechanism for us. And if you want to arrange, let's say, a FIFO structure, Kafka would be good. But maybe Kafka is an overkill. Maybe Kafka is an overkill for us. I'll tell you why. Let's see. So Kafka guarantees the order within a partition only. So in Kafka, you have multiple partitions. So let's say you have 10 jobs. You have 10 jobs. And you want to arrange these jobs in the order of their schedule time. Now, are you going to distribute these jobs in different partitions? No. Why? Because different partitions don't guarantee the order. In Kafka, the order is only guaranteed in one partition. So if let's say you have to run 10 jobs in the next 1 minute, you have to put all of the 10 jobs in the same partition only. If you have to put all of the same jobs in the same partition only, then what is the point of having multiple partitions? What will you do of this particular feature? And of course, there is a lot of overhead with Kafka. You have to manage a lot of things. Learning curve is there. So maybe Kafka is not the best solution for you. Okay. What is the second option that you might think of? Okay. Second option would be that, okay, you have to arrange things in ordered fashion. A Redis sorted set can be there. A Redis sorted set can be there. This would be a good solution, but again, slightly a bit overkill. Why? Because Redis sorted set doesn't provide you a retry mechanism. So of course, if you are going to put the next 1 minute jobs, let's say in the next 1 minute, you have to run 10 jobs. You put all of those 10 jobs in a queue. Then there needs to be a consumer. You have produced the data in the queue. You need to have a consumer. If the consumer is not able to pick, there is no retry mechanism directly implemented. You have to implement your own retry mechanism altogether. That will be an overhead, but Redis sorted set would be a okay solution, good solution. No problem there. But you don't have a dedicated retry mechanism definitely present. So what are the other options? Go with a simple queue. Just straightforward simple queue infrastructure, like use something like RabbitMQ, use something like Amazon simple queuing service. All of these have simple setup, simple infra, retry mechanism implemented, able to handle good scale as well, right? So considering that we want to have good scale and we can use some managed services, so SQS can be a good solution to go for, right? So this is how our new infra is, or I would say new design is going to look like. That let's say the client sends the request, goes to the API gateway, from API gateway goes to load balancer, and the request for scheduling a job goes to the scheduler service. Scheduler service is going to dump this in some database. We are yet to decide on the final database, but whatever is this database, from this database, somehow our system is going to query every minute. Every minute we are going to query upcoming set of jobs. So I'll say that I'm going to have a watcher service here. This is a watcher service. Watcher service is going to be responsible for querying our database every minute, or we can keep it a configurable value every 2 minutes, every 30 seconds, whatever configuration you want, that query our database every 1 minute altogether. Fetch the upcoming set of jobs. Once you have the upcoming set of jobs, what you can do is you can enqueue the jobs in the Amazon SQS service, which will be a simple queue, right? So the next 1 minute set of jobs, you order them in their time, and then you are going to dump that in the SQS. Okay. And now from SQS, we are going to pick these jobs. We are going to technically pick these jobs. So there is going to be another dedicated executor service. There is going to be another executor service. What this executor service is going to be responsible for? Executor service is going to pick the job from SQS. Job means the job payload. Job payload will be having what Python script to run and what are the parameters to run for it. Okay. It will pick the job from your queue. Then it has the Python script ID. It is going to fetch the Python script from your S3 storage, because we have dumped all the Python script in the S3 storage. Whenever we are going to get a schedule, this schedule is going to dump the schedule in the database, and this schedule service is going to dump the Python script inside your Amazon S3, right? So when we are expected to run the job, this executor service is going to pick the job from my queue and see, oh, this job is expected to run this particular Python file. Let's download the Python file from S3. And then, is this executor service going to run the Python code in itself? No, this should not run the Python code. Ideally, what this executor service is going to do is, this executor service is going to boot up a new Docker instance or a new Docker container. Inside that Docker container, it will load the Python file and run the Python file. Why? The Python file can contain malicious code. It can contain some wrong code which can choke the complete CPU altogether. Maybe there's a fork bomb that is written. So you don't want to block this particular executor service altogether. This executor service, what it is going to do, it is going to run a Docker instance altogether. To run this Docker instance, again, if you have to run 1 billion jobs or 10 billion jobs, running the Docker instances inside the executor service might not be the best idea. So what you can do is you can use something like ECS for this. Elastic Container Service. It's an Amazon service which can help you to manage all the containerization stuff for you. You can read separately about it. But this executor service will be responsible for creating a new ECS instance, or let's say there are some already set up warm ECS instance that you can use, and then just boot up a Docker container inside those ECS instances and run your Python file there. So again, explaining the flow of the system. Load balancer is going to redirect the request of creating a job. Load balancer is going to redirect the request of creating a job inside the database, and it will dump the Python file inside the S3 storage. Once that is done, there is a watcher service. This watcher service is going to fetch the upcoming jobs for the next 1 minute from the database. Once this has been done, it is going to enqueue the jobs in SQS. So let's say there are 10 jobs, J1, J2, J3, and so on, J10. These are enqueued inside your SQS. And from your SQS, there is going to be a consumer, right? There's going to be a consumer service, which we will call as executor service, which will one by one pick the jobs. You can horizontally scale the executor service also, so that you can pick multiple jobs together also. But while picking the job, it can check that is the current timestamp and the job timestamps when it is expected to run, are they almost close or not? And once it is, then it can try to pick it up. Once it has picked it up, then it is going to boot up a new Docker instance or Docker container using Elastic Container Service and run the Python job there. Once the Python job runs and it gets the status from the Elastic Container Service, this is going to make an API to the job scheduler service that, okay, we have received an update on the last run of the job, and that scheduler service will update the run status inside the database. This is going to be the flow that we are going to have. What this flow benefits is that because we are going to enqueue all the jobs, if we have a huge load of job in the next 1 minute, then our system is not going to be bombarded. We can scale the consumers of the executor service in a way that, okay, we are able to cater the load accordingly, right? If you have too much amount of load, then you can scale the executor service accordingly, right? But still, if there is a lot of requests coming up, then those requests are going to wait in the in the queue, right? This is going to wait in the queue, and this will also guarantee us the delivery, that once this has been loaded in the queue, this will be technically correspondingly delivered as well, right? So this will help us to also maintain that at least once delivery, that we are able to run the job at least once altogether. There is a question that can come to your mind. Let's say at 301, or let's say at 305, our watcher service queried the database to fetch the next 1 minute set of jobs. So it got J2 and J1 and J2. Let's say immediately at 305 only, when watcher service was querying the database, a user also scheduled one more job. Let's say J4 for 305. Same time, at the same point of time, when my watcher service was querying my database to pick J1 and J2, at the same point of time, or let's say almost about at that point of time, one more user scheduled the job for 305. Then what? Then J4 will not be picked. Why? Why J4 will not be picked? Because our watcher service has already swiped our database and it already got J1 and J2. At that point of time, J4 was not present. So what can happen? So this can be a manual handling that you can do, that in case you are trying to add a job, whose run has been already added, or whose run swipe has been already done by watcher service, then the scheduler service can manually add that in the SQS. Okay, this will be kind of like a failover situation, or when the next run will happen at 306, it will also query for all the pending jobs before 306 also, that was there any job that we were not able to pick up because of any XYZ reasons at 306, because this is a guarantee that you can give, that okay, if you schedule the job at the same point of time, then probably will take a minute to run your job. So again, this can be dependent on what kind of an SLA you are going to provide, that in the next run we will pick all the pending jobs also. But a better way would be that, why do you want to wait? The scheduler service can check that, okay, the timestamp of running the job has already exceeded the last swipe timestamp. So let's manually add that into your simple queue service. Now the interesting discussion is coming back to what database choice you need. Now just think about it. Mostly we will fire a read query every 1 minute. We can make it configurable also, that let's say it is 2 minutes, or let's say every 5 minutes, or whatever it is. So we're going to fire a read query every 1 minute. So there is not much read load on the database. Like every minute, if you are firing a read query, right? So like in an hour, you're going to fire 60 read queries. That's very easy to handle for most of the modern database. So we don't have to bother a lot. But the problem that will come is, but whenever we query, we need to filter the upcoming jobs to run. This job schedule table is going to be a long table because it will be having a good amount of schedule. Let's say you always keep 5 upcoming schedules for every job. Let's say there are 10 jobs from J1 to J10. For every job, you keep the next 5 schedules already prepared in this job schedule table. That what are the next 5 schedules of this table? Of what are the next 5 schedules of the 10 jobs that you have? Think about it with respect to a billion jobs. If you have, let's say, 10 billion jobs, or let's say 1 billion job only, then you will be having approximately 5 billion entries at every point of time, because you are keeping 5 next runs of every job. Can I say that? So from this huge table, every minute you have to query the data, but from this huge table you will have to query the data. In that case, what you need? If you do a linear search like a scan, that will be very slow. That will be extremely slow, because 5 billion queries, and this is with respect to 1 billion. If you have 10 billion job, this will be 50 billion entries. 50 billion entries you won't be able to do in very fast, like probably, because you know that in 1 second you won't be able to do that, right? So a complete DB scan can be very slow, very slow. So what do you need? You need an index which can order the data based on the run timestamp. That okay, we are at 305. We want to query the jobs that are expected to run between 305 and 306. So how about you do an index search, because your data is ordered in the form of timestamps, right? In this way, you do not have to do a linear scan. Whatever index you have, it can query the data. Let's say even if it does simple binary search also, that will be a relatively faster data to query. So definitely we need an index. We need an index altogether, right? Now, and again, the database choice can also, I would say, drive this. You need an index which will help you to do a range query. Now, can I say this is a range query? This is a range query. Okay. So if this is a range query, then of course your key value stores like something like Redis won't be the best solution to go for altogether, right? Choices can be there that you can, let's say, pick up a time series DB, but we want to prepare a database that is good for most of the situations that we have. So let's see what solution I propose. Now, considering that we do not have a lot of reads, like in 1 minute you do 60 queries for a read. So definitely it's not a read heavy system. Compared to the number of reads, writes are more. Writes are more. So you can say the system has a lot of writes, as there will be status updates for the job runs, and also we need to add jobs for the next run schedule. Okay. So definitely a more write heavy system compared to the reads. Can I say that? It's relatively a more write heavy system. If it's a more write heavy system, generally a good choice can be what? Something like Cassandra, right? Cassandra is generally recommended for a good write heavy system. Why? Because of its, I would say, quorum based architecture, right? Its last write wins architecture, and so on. And another choice can be something like DynamoDB. If you have not read about Cassandra, or if you have not read about DynamoDB yet, I would recommend you to read about Cassandra and DynamoDB. We will discuss this in a separate session, that what Cassandra is, what DynamoDB is, and etc. But Cassandra and DynamoDB can be good choices. DynamoDB is a AWS managed database service, right? So before I complete the conclusion that okay, we go with Cassandra and DynamoDB, let's try to eliminate a few. You might be having a question. Hey, why not a simple PGSQL or a MySQL instance? Why not a simple PGSQL or a MySQL instance? Because in PGSQL or a MySQL instance also, you will be able to handle good load, and indexing capabilities they also have, right? So why not a RDS? Because generally RDS is not going to be picked just because it has indexing capabilities. We need RDS when you have to do normalization. We don't see any data normalization concepts here, right? We can keep the data as it is. No normalization heavy data is there. There is no asset guarantees that we need as of now. So like picking up RDS will be not required as such, right? So we are not going with RDBMS. So some no SQL choices we can explore. So Cassandra and DynamoDB both are good no SQL choices, right? We could have used Redis, but the lack of indexing and the problems with range queries, Redis cannot go, right? So we have discarded RDS. Why? Because no asset requirements, no normalization requirements. So managing RDS won't be required altogether, right? If you want, you can go with RDS, right? If let's say, if I tell you a couple of numbers, right, you might be thinking that, okay, if I take RDS, let's say, let's not go with what Sanket recommends, right? Let's say I take an RDS instance. Let's say I take an RDS instance. Let's say PGSQL. Okay, what amount of load will we be able to see? So if you have to handle, let's say the writes, if you have to, let's say, handle the writes, and assuming that you have deployed your RDBMS instance on AWS, right? Then very easily you will be able to handle 10 to 20,000 uh, writes on a single node of RDS very easily, and reads you will be able to handle 50,000 altogether, right, per second. I'm talking about these numbers as per second. That if you have a good, I would say, powerful node on which you have deployed your AWS RDS instance, then 10 to 20,000 writes you can definitely handle in a day. But you don't need that because you don't have asset requirements, and DynamoDB will help you or Cassandra will help you having more, I would say, features altogether, right? That's why I am discarding RDS. So in case somebody asks why not an RDS, you can tell RDS can be a good choice if you have deployed your RDS on a good instance where, let's say, you are able to handle 10 to 20,000 writes, and generally you are able to handle 50,000 reads per second. It's not bad. It's definitely not bad. Why? Because if you see what amount of I have done that calculation later. I'll show you that as well. Um, if I show you the calculation, okay, so you can see I've done the calculation. So we won't be handling a lot of writes, right? So 50,000 writes per second would be a good choice for us, right? But we can do slightly a bit more better by using some NoSQL. So Redis we have discarded because range queries can be a problem. So the option that we are left with is Mongo, Cassandra, DynamoDB, these kind of storages, or sometimes time series DB. Now we can use any one of these, as the writes are also not much. You can see worst case you are going to have 10 raised to the power 4 writes per second, considering there are 10 raised per 9 jobs will complete in the same day. Just think about it. If there is 1 billion job, 10 raised per 9 jobs that are completing in a day, then how many writes you have to do per second? The number of writes will be directly proportional to the number of jobs you are going to execute per second. Because let's say every second you execute jobs and the last second executed jobs have completed. That will be the maximum throughput that you need. So 10 raised per 4 writes per second you need. Even a MySQL instance can handle 10,000 writes, 10 to 20,000 writes. So if you scale that MySQL instance well, you will be able to handle that. But if you have a 10 raised per 4 writes per second, right, altogether, any one of these NoSQL instance will be able to handle it. Even Mongo can be used because Mongo also has indexing capabilities, right? Mongo also has a distributed architecture altogether. So even Mongo can be used, right? We are going to consider DynamoDB. Why? Couple of features that DynamoDB provides. First, DynamoDB is a AWS managed service. So a lot of auto scaling aspects and everything is going to be managed by AWS. Good replication support that automatically DynamoDB gets. That's good. DynamoDB provides very high throughput, very low latency. So DynamoDB we are going to consider. In case your ecosystem or your company ecosystem supports more Mongo, or you are more Mongo first approach or a more Cassandra first approach kind of like company, you can do that. I am keeping DynamoDB because of these reasons, that I have eliminated already RDS. I've already eliminated RDS, right? I've eliminated Redis altogether. Then among the remaining set of choices, I feel DynamoDB is slightly more better. Why? Because DynamoDB gives you a configuration based approach that if you want, you can increase the write throughput. If you want to increase the read throughput altogether, right? That's why you are going to have a lot of benefit if you use DynamoDB, right? So let's say how our schedule table is going to look like. So in DynamoDB, everything is a table. You have a partition key and a sort key. So based on this partition key and a sort key, the complete searches are going to be relatively more optimized as well. If you need extra indexes, then you prepare some global indexes altogether. So a lot of features you are going to get DynamoDB, but Cassandra or Mongo can also be a good choice here. You can tell that in an interview. Now this part, which is slightly a bit more deeper data dive into database, this might not be required in an interview. I'm doing this because I don't want to make these sessions only for interview perspective. Your regular SWE work should also be benefited. So let's say you have this job schedule table. Remember the job schedule table. So here you can store a time bucket, right? This is the time when the job is expected to run. You can see this time is a Unix timestamp, right? And then what should be your partition key? Because if you are using DynamoDB, then in an interview, there might be a chance that people can ask you that, okay, if you're using DynamoDB, what should be your partition key and what should be your sort key? Okay. So assuming that we have jobs to run, we have daily jobs to run, we can keep 24 partitions, one for every job. Now just think about it. DynamoDB works on this partition based architecture. So what you can do is you can have 24 partitions. In each partition, you can store all the jobs that is going to run for the next 1 hour. So that means when you are going to query your corresponding next job in a minute, then you only have to query one single partition. Are you able to get this point? Right? So think about it. Let's say all the jobs that are expected to run from 3 a.m., all the jobs that are expected to run from 3 a.m. to 4 a.m., right? They are present in, let's say, partition P3. So when you have to get what are the jobs that we are expected to run in next 1 minute, you only have to query the partition P3. You do not have to bother about the remaining partitions. And how you figure out that? How you can figure that out that, okay, which partition you have to query? Let's say you have you have to find out that from 305, from 305 to, let's say, 306 in the next 1 minute, what all I would say data you have to technically fetch, or let's say what are jobs are scheduled. You can very easily use this Unix timestamping approach, right? Let me show you. So what you can do is you can keep 24 partitions. In each partition, we will keep the job schedule to run in that order, right? So every partition will be having the data in the right order also, right? So to keep the data in the order, we are going to provide a sort key. What should be our sort key? So in DynamoDB, it's a constraint that the combination of partition key and sort key should be unique. So let's say if I keep the time bucket as a partition key, if I keep the time bucket as a partition key or the timestamp to run as a partition key, what should be the sort key? I can keep the sort key as something like this, right? So how can we make it unique? We can combine the timestamp with the job ID to make a unique sort key. So you can see this job ID is there. You can see this is the job ID, and this execution time is your sort key. You can see it has the club of the timestamp when you want to run the job, and you have the job ID. So this is your partition key, this is your partition key, and this is execution time is your sort key, right? And you can see now both of them together are unique. Both of them together are technically unique. Now, I would like to answer one more thing before we go ahead. Okay. So now how can we calculate which partition a schedule entry is gonna go, right? How can we decide? Because now just think about it. If let's say all the jobs that are going to run from 3 a.m. to 4 a.m. are going to be present in P3. So when we are going to create the schedule for the job, how we are going to decide which partition to pick up? So whenever we are going to create the schedule for the job, we will be having this timestamp, right? That when are we expected to run the job next? Using this timestamp, you can calculate the partition. How? Let's see. So what you can do is you can take the timestamp because it's a Unix epoch time. You can divide that by 3600 and take a floor value. You can get the floor value. This will give you the floor hour. So for example, you are expected to run it at 305. You are expected to run it at 305. This floor division will give you 3. That is 3 a.m. And then you convert it back to Unix epoch time. You can see you convert it back to the epoch representing the nearest floor hour, right? So for example, if the time is this, let's say this is the timestamp of the job to run. This is representing what? 2025 January 27 2:35 p.m. 14:35 means p.m. Okay. So what I do is I divide this by 3600. You get this value, right? And then I multiply this with 3600 again. You get this value. This value is representing 2025 January 27 2 p.m. So can I say I have reduced it to the nearest hour? I've reduced it to the nearest hour. So when we are going to create a job schedule using this particular formula, you can decide which partition you want to redistribute your job to. Okay, that is going to be something that you're going to have. Who will create these schedules? Because what is this schedule table? Remember, we talked about the fact that this schedule table is going to have the data of the next 5 runs. Who will add the data of the next 5 runs? I'm going to talk about that. But I believe this point is making sense that what we are doing here. Okay. And what consistency model we are technically going to have? We are going to have an eventual consistency model. We can very easily support that with DynamoDB. So eventual consistency would be enough for us, as even the job status changes after some time, we are okay with it. So DynamoDB can very easily handle your eventual consistency model also. That's very much, I would say, in terms with our non-functional requirements. Now, what write throughput we are going to get? So on an average, let's say we can assume that when job completes, the update for that run in the same schedule table, or we create a separate run table. So here you can see I have described that we can create a separate run table, and that's in line with our initial discussion also, that whenever a job completes, we are going to store its past run in a separate run table. We are going to store its past run in a separate run table. So if I come back, okay, so let's consider a separate run table which is partitioned on run ID. So whenever we run a job, we create a unique run ID, okay, so that we can uniquely identify every run. Assume we have 10 partitions for run table. Now for even the run table, let's assume separate partitions altogether, right? Each partition by default can handle 10 raised to the power 3 writes per second. So this is the default configuration. So in the default configuration, one partition of DynamoDB can handle approximately 10 raised to the power 3 writes per second. Again, knowing this is not mandatory, right? I know the numbers, so I put it here because I mentioned that this particular discussion is more helpful for you when you're actually doing your SWE job rather than in your interview, but I want to keep it a deeper dive. So a default partition of DynamoDB can handle 10 is per 3 write per second, but you can increase it. So there is something called as WCU, write capacity unit. It's kind of like a currency. It's kind of like a currency. So in every partition, you can decide how many WCUs you want. The more number of WCUs you spend, the more write throughput you get. It's kind of like that. Okay. So with that, if let's say you have 10 partitions of the run table, if you have 10 partitions in which the run table have this, all of this thing, then with that, you can very easily support 10 raised per 4 writes per second, because each partition of DynamoDB by default supports 10 raised per 3 writes, right? So if by default you are having 10 raised per 3 writes per second, then 10 partition, 10 into 10 raised per 3, you'll be able to very easily handle 10 raised per 4 writes per second. Where is this 10 raised per 4 writes per second number is coming from? Just think about it. You were having, if let's say 1 billion jobs you are having, then you were having 10 raised per 4 jobs that you can run, right? You were able to run 10 raised per 4 jobs per second. Assume 10 raised per 4 jobs are running per second, and every second we are getting updates also of the all those last 10 raised per 4 jobs that you have run. Like every second you complete the jobs. So 10 raised per 4 jobs ran in the last second, and this second we got their update. So we have to write their status update in the run table, that what was the status of the run, what happened with the run, and so on. So we will be able to handle this much amount of throughput. Okay. So this is gonna be kind of like a slightly more deeper dive, which will help you there. But if you want to increase the write throughput, you can spend more WCUs. So there is a concept of RCUs and WCUs in DynamoDB. RCUs is read capacity units, WCU is write capacity units, things like that. Okay. So that is going to be something that you can technically do here. Just again mentioning that, as I mentioned, I want to keep these sessions even good for a SWE job perspective as well. So there is a sample code that you can see that I have written for preparing a schedule table. It's a rough Python code, you can check. Okay, so you can see there's a create table function. We are using a Boto3 library in Python, which is kind of like the library, which is kind of like the SDK using which you can access a lot of AWS services. Okay. So you can decide the corresponding region, and DynamoDB is the resource that you're going to have. So what you can do is you can say dynamodb.create table. You can give a table name, and then you can give the attributes. So here, this is going to be the partition key. Time bucket is going to be the partition key, and this is mentioning as range. So this is the sort key. So execution time is going to be the sort key. Okay. And you can see here, you can define the write capacity units and read capacity units, the RCU and WCU. You can configure it accordingly. I've just adjusted this at 1010. And then whenever you have to insert a record, what you're going to do is, in your corresponding table, you're going to do a put item. The item is going to have a time. It is going to have execution time. Execution time is going to be your time. This should be time bucket here. This should be time bucket. Time bucket hyphen the job ID. This will make combination of partition key and sort key unique. You'll be having a job ID, the user who created, the status of this, and attempt, and so on, like other data you can have. Whenever you have to query, what you can do is, you can say that what time bucket you are in, right? So you can use the time bucket parameter to query for the time bucket. You have to query current and next hour jobs. So again, the same logic you are going to apply, that you are going to get the next time bucket and the current time bucket. So let's say your job was expected to run at 3:05. This formula will give you 3 o'clock. And if you add 3600 to it, this will give you 4 o'clock, right? So once you have the start time and the end time, like the next 1 hour jobs, right, then you can query using this particular code. If again, you can configure it, instead of next 1 hour, you can just take the next 1 minute of jobs. So the same function can be used to also use at multiple places where you want to fetch the next one kind of like minute of jobs. Okay, so you can see, you can say equal to current timestamp, and the next response is going to be equal to the next timestamp, and then you can return those jobs. So just a rough code I have prepared, right, so that you can have some idea. This rough code will be generally going in a design doc when you are proposing this feature to your bigger organization when you're working. This coding implementation is not required in an interview. Okay, similar coding implementation for the run table as well. You can see in the run table I have not prepared any sort key as of now, right? So because in the run table, what you have to do, you just have to update the job status. So you know the job ID, right, that you have to update the status. You don't have to do any kind of range where your searches is not going to matter a lot. So just using the I would say partition key, we are going to use the job ID and just update it with respect to job ID also. You can see update run status, it will take the job ID and it will take the corresponding status, right, that you can update. There's a function get run status. So if you remember, we were having an API that can give us the status of the job. This function can be triggered by that particular API altogether as well. Okay, something like this. Now, slightly a more deeper dive, again, might not be required in an interview, but would be good as a software engineering design doc. How much load we are looking for our SQS queue. We talked about the load that our database can take, because 10 partitions for run and 10 is per 3 writes per second. That also configurable, right? But what about the SQS queue? Generally, in the very good configurations, you can see there is a Stack Overflow article I have attached. I'll deep down in this article, but let's see what is the requirement that we have. So we are expecting that 10 days per 4 jobs in the worst case will be coming every second. So we'll be enqueuing 10 days per 4 jobs per second, and that will be getting consumed. And every 1 minute we will be enqueuing jobs. So every 1 minute we are going to enqueue jobs for the next 60 seconds. In every second, if there are 10 days per 4 jobs coming, that means in 60 seconds we will be having 10 days per 4 into 60 jobs coming, which will be 6 into 10 days per 5. We can take a upper limit of 10 days per 6 jobs. We can take a upper limit of 10 days per 6 jobs, that every time when our database is queried for the next 1 minute run, in the worst case, you will be picking 10 days per 6 jobs. Now, if we would have kept a Kafka cluster, throughput of 10 days per 6 messages per second would have been relatively very easy. SQS doesn't support that very easily. You can see this is a Stack Overflow article which has the right data mentioned for a FIFO queue on SQS, that if you implement batching with high throughput nodes, that will of course cost you a bit more, then you'll be able to approximately support 30,000 messages. So the amount of throughput that we are looking at here might not go very well with a single SQS queue. So definitely you need multiple queues. If you do not want to spend on multiple queues at this point of time, Kafka would have been slightly a bit more better. But again, the Kafka metrics are also based on that you are able to partition the data. We are not able to partition the data much, right? So what you can do is you can have partition for every 10 seconds, so at least 6 partitions you have. And then for those 10 seconds, the same order of FIFO you can keep in your Kafka cluster. So this choice can be taken, that SQS might not be having these high numbers for us. So Kafka can be a good alternative, but in an interview, you are not expected to know these numbers. right? I'm just taking it for more deeper dive. So because 30,000 messages can be handled by one SQS, that also with batching and high throughput node. So you need more queues, approximately 30 to 40 more queues probably you need. Okay. So that's for a FIFO. That's for a FIFO configuration, not for a standard configuration. For standard configuration, you can have good amount of scaling that you can expect. Okay. So this is coming from a Stack Overflow article. So if somebody asks you that how much load your SQS queue will be able to take, you can say one queue can take 3 into 10 is per 4 kind of a load altogether. Okay. Now, one question that might be coming to your mind is that let's say sometimes it can happen that your executor service takes the job more than once, right? Let's say it picks up the job from the SQS queue, but it is not able to send the acknowledgement to the SQS queue, right? Or let's say some failure happened here. Think about it. It picked the job, it started running the job in the ECS container, but this machine went down. When this machine went came up, what it will realize, oh, we have not dequeued that from the SQS. It will again pick up the job and put it inside your ECS. This can happen, right? You have to be prepared for your failure scenarios. So how can you try that a job which has already started running should not run again? A good straightforward solution can be the implementation of idempotency, right? Idempotency can be useful. You can keep a unique idempotent ID, right? And then avoid this re-triggering altogether. If in case you don't know about idempotency, read about it, what idempotency is. This will help you to avoid at a lot of places whenever you want to avoid any kind of a re-triggering. Okay, so idempotency would be a good solution for that. This can be a follow-up question that can asked in your interview as well. How can you avoid it? Now, an interesting question is, what if a job run entry came and we have already that job in the DB entries where the job run would have been considered, right? So again, this is already what we have discussed, that in case the job swipe already happened for the last minute and your job entry came later. So what you can do, you can pick up in the next run, or you can ask your schedule service only to enqueue that job. We have already considered that. Now, somebody can even ask you to take a deeper dive on the job schedule table. This is going to be interesting. That I said that in the job schedule table, we can store the next 5 upcoming runs of the job. Whenever job execution is going to complete, we are going to update that in the run table. Run table is a separate table. Now, when the first time a job schedule comes, it gets registered in the jobs table or it gets stored in the jobs table. Let's call it as stored in the jobs table, right? That means, let's say I'm a user, I created a job entry inside my system. So for the first time when I said that, hey, please take this job and run it at every 5 a.m. in the morning every day, so that's the new job entry. It will get stored in the jobs table. When a job completes the run or has success, failure, whatever it is, then we store that in the run table. In the job schedule table, we store its schedule, upcoming schedule. So when the entry comes in the job schedule, the entry or a data entry in the job schedule table can come because of two reasons. First, when for the very first time a job is scheduled, then we create the first entry in the job schedule table. Let's say today is what? January 29th, 11 p.m. I went to my platform and I said that, hey, take this job and run it every 5 a.m. in the morning. So this job entry gets in the jobs table. Now, the moment it gets entered in the job table, we have to schedule its next 5 runs. What will be the next 5 runs? Next 5 runs will be run it at 5 a.m. 30th of January, run it at 5 a.m. 31st of January, run it at 5 a.m. 1st Feb, 2nd Feb, 3rd Feb. That will be the next 5 runs. So we have to create those next 5 runs the moment we register the job for the very first time. That will be the first type of entry that will come in the job schedule. What will be the second type of entry? When a run happens, let's say now 30th of January 5 a.m. came up and the job actually started running. So there were 5 entries. Now there are only 4 entries because we have picked one entry altogether. When that job run has started, then we have to add the next run for 4th of Feb also, because we always want to keep the next 5 runs. So if 30th Jan, 31st Jan, 1, 2, 3 Feb, 5 are there. The moment 30th Jan job is picked, we would like to either update an entry, the same 30th Jan entry we can update, or maybe remove the 30th Jan entry and add a new entry inside our job schedule table that, hey, the 5th run is now the 4th Feb run. 4th Feb, 5 a.m. in the morning. So these will be the two type of writes that can comes inside our job schedule table. Cool. Now, considering that, now you might be having a question. Who will update this job schedule table? That when the first time job registration comes up in the jobs table, then we have to create entry. And every time a run happens, then also we have to create an entry. For this, you have two choices here. One cool choice would be to add a job trigger, or I would say a database trigger. If you have a database that supports trigger mechanisms, then what you can do is you can set up a trigger that every time you insert something in the jobs table, you update the job schedule table. Or whenever you create a new run in the runs table, then you update the job schedule table. You can add triggers, right? Can I say that? We can add triggers. But there are problems with triggers. So the problem with triggers, there's a significant problem with triggers is that triggers are stored procedure that runs the moment an event happens. The problem with triggers is it's a synchronous execution. If you are doing a transaction on your database, then in the same transaction, the trigger code also runs, right? And because it runs immediately, it can add latency altogether to your write operations. Okay. But you don't have to go with any network, I would say, like any kind of a network interaction, you don't have to do, right? So that's a good thing. So a lot of time people write logics in their stored procedures if they do not want to add any network latency. But we do not have a issue with that here. So the other thing that you can do is you can use the mechanism of change data capture. If you don't know about change data capture, try to read about it. We can discuss that in a separate session. You can say change data capture is a mechanism which can help you track any changes that happened in your database in a more asynchronous fashion. The moment you introduce asynchronicity, that means you are going to improve the overall latency altogether, right? This is not going to add any overhead to your write operations. So adding a change data capture to your jobs table and the runs table to update the job schedule table can be very good. And interestingly, because we have used DynamoDB already, DynamoDB streams can be a good way to handle this. So this will improve your scale, more preferable, considering that it's asynchronous. You can use a third-party solution like DBZM as well, but change data capture would be good. So at any point of time, whenever you have to react on, let's say, any changes in your database, until or unless that reaction is very much closely related and you have to do with a triggered or a stored procedure inside your database, it is good that you implement a CDC altogether. Then one more question can come to you in an interview: how you can support priority. Very easily you can support priority. You can have different queues for different priorities. So if let's say you define 5 priorities, 1 to 5, you can have 5 class of queues depending on what kind of scale you can have. You can have different capacity of the queues as well, and every job will be having a priority number attached to the instance. You can send that to the corresponding queue. That would be something very straightforward. Now, how the watcher service can be implemented, we have not discussed this, that how this watcher service is going to, because what is this watcher service going to do? The watcher service is going to query our database every 1 minute, that give me the next 1 minute job. How can you run this watcher service to query this database every 1 minute? There are a couple of solutions. Again, one solution can be you can use some third-party libraries, like in Python you have a scheduler library. But a good preferred solution would be to use crons, right? Would be to use crons. Now you might be thinking why we are not making the whole system as a cron job. Like if somebody gives you a job scheduler, you can say, I can set up a cron and run the job again and again. That would have been a straightforward solution for a job scheduler. Why we are doing all of this? Because we don't want to go into the hassle of writing a cron job again and again for every job. For 10 billion jobs, you cannot write cron jobs, and then maintenance of those jobs is going to be a hassle, right? That's why we don't pick that. But cron is going to be useful for us for making our watcher service. What is cron? Cron is a Unix utility for scheduling scripts at specified intervals. You can prepare a schedule in the cron tab file. So there is a cron tab file in Unix, in most of the Linux systems. You can update that file, and you inside that cron tab file, you can mention a schedule and a script to run. So how the cron schedule formatting is done is something like this. You have 5 stars that represent what is the schedule, and after that you can mention the script that you are expected to run. So the first star represents the minutes, that what minute you want to run the job at. The second one represent hours, then third one day, month, and the day of the week. So for example, if you say 5 stars, it's like run it every minute of every hour of every day of every month or of every date. So that's equivalent of saying every minute. If you say 0, 4 stars, that means run it at the 0th minute of every hour of every date of every month of every day. That means you have to run it every hour. If you say 00, triple star, that means every day at 12 a.m. because 0 means 0 hour, that is 12 a.m. When you say 00, double star, and let's say you say fry, FRI, or you can even say something like what, 5. You can even say 5 here. That means at 12 a.m. on Friday, that means 0th minute of the 0th hour of every Friday of every month, right? You have to run a job. If you say 001 double star, that means at 12 a.m. on the first day of the month. You can have some more complex expression as well. For example, you can say star by 5. Star by 5 means you have 60 minutes, right? If you say by 5, that means every fifth minute you have to run a job. If you say 5 for this, that means every day you have to run a job at 4. 4 means the hour, 5 means the minute. So at 4:05 every day you have to run a job. Okay. So that's how crons are technically written. So you can, what you can do is you can have a process in your watcher service, which you can define that, okay, every minute you have to run. So you can write star, 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 and whatever program you have written, cron will automatically run every minute from your watcher service, make a call to your database, fetch the next 1 minute of jobs, and enqueue that in your queue. One last important thing, that how can you handle dependent jobs, right? Now, to handle dependent jobs, you might want to take a deeper dive on how jobs table is going to look at. We have already discussed this, but I'll just go through it once again. The partition key is going to be something like this. There is a job ID that we are going to keep. There is a schedule expression. Like, now just think about it. There will be a UI platform. From the UI platform, the user will say every day 10 a.m. So how will you store that in the database? Every day 10 a.m. if you have to store, you will store also like a cron expression only, right? You cannot store every day as a string, right? Cron expression represents the time schedules in a much more shorter format. You can keep a status of the job, that the state job is disabled or enabled. So if you remember, there was a functional requirement that we can mark a job enabled or disabled. So if you keep a status in the jobs table, that can very easily handle that. You can have a created at and updated at timestamp, and you can have a dependencies list. This dependencies list can keep the dependent job IDs. So whenever you are going to run this job or create the from, let's say from the job schedule, you picked up the job, right? Then what you can do is, when this job is about to be queued, we can check the list of dependencies here and see whether those dependencies are marked completed in their last run or not. How can we fetch the last run from the run table or not in their last run? When creating a new job, we can use this dependency list to show error if the user puts a run schedule conflicting the list here. So for example, there was already a job A after which B and C are going to run. Now let's say user comes to your platform and says that, okay, I'm going to schedule a job D, but they put a schedule which is conflicting with B or C. Then what you can do is, you can, before you make an entry of D, you can check the dependencies B and C and A, and let's say you can topologically sort these dependencies based on the schedule time, and then decide whether D is gonna be conflicting for them or not. So let's say if you go to Azure Data Factory, in Azure Data Factory, if you have a dependent job and then you try to schedule a new job that is conflicting with that job's schedule, it throws you an error. So if you have to implement that in that case also, this dependencies list can be very good, and you can write a custom topological sort that can handle this. So even a dependent jobs, right, that you have, you can handle it in a very easy way using these dependencies list. And that's more or less that is going to be required for most of the levels if you are going to expect, if you are going to be expected to design a distributed short job scheduler altogether. A few features that we have like not gone a very deep dive into because those were good to have features. For example, resource allocation configuration. The executor service can actually take a payload from your database that what is the configuration expected for this particular job, and then based on that configuration decide what type of elastic container it has to boot up. So that also can be stored in your database, which you can pick from the DB, and executor service can be allocated this role altogether. Okay. Recurring jobs we have handled. At least once guarantee we are able to give because of the queuing infrastructure. Python script handling we have done that. I have not discussed the upload flow, that how Python script will be uploaded. That's a very basic flow altogether, but we are going to keep that into S3, right? Manual trigger support. We have not discussed much on the manual trigger support, but that is going to be very easy. Whenever a manual trigger happens, what you can do is you can create a brand new run apart from the job schedule. So an immediate run you can make it. The request goes to the scheduler service, picks the job from DynamoDB and enqueues it immediately in the queue. That will be a manual trigger, which will be again very straightforward. So most of the features we have technically kept. 7 point also we have discussed, and that's more or less, I guess this would be enough for you to discuss in 1 hour, right? You can see most of the discussion we have wrapped in within 2 hours, right? A lot of deeper dives we went into around the numbers, but those might not be required for an interview perspective until unless you are interviewing for a senior role altogether.